Hello, everyone. Welcome to another session of ILTA Physics online problem solving. Today, we're going to work on problems involving inelastic collisions. An inelastic collision is a type of collision where two objects stick together after they hit each other and move as a single unit with the same velocity. To solve these problems, we use the law of conservation of momentum, which applies to all collisions, along with the fact that the objects combine to move at a single common velocity with a total mass equal to the sum of their individual masses. Today's problem set covers inelastic collisions happening horizontally or vertically, as well as cases where objects come to a complete stop after the collision. First, let's briefly go over the theory behind inelastic collisions. Let's summarize the conservation laws for elastic and inelastic collisions. Consider a case where two objects move toward each other and collide, as shown in the diagram. If the two objects move separately after the collision, it's an elastic collision. If they stick together and move at a single velocity, it's an inelastic collision. Generally, we use a prime symbol to distinguish the velocity after the collision. As you can see in the diagram, in an inelastic collision, the objects become one mass and move with one common final velocity. The law of conservation of momentum holds true for both elastic and inelastic collisions. This means the total momentum before the collision equals the total momentum after the collision. We can write this as momentum initial equals momentum final. In actual problems, we use the momentum formula to calculate each momentum as the sum of the products of mass and velocity for the objects before and after the impact. For the inelastic collisions we are focusing on today, please pay close attention to how the equation is set up for the state after the collision. The total mass becomes the sum of all individual masses, and the final velocity is a single shared velocity. Now let's solve some problems involving different types of inelastic collisions. Problem number 30 describes a football game where a receiver jumps vertically to catch a ball flying toward him horizontally. If the receiver catches the ball at the very peak of his jump, what is the velocity after the catch, and would he feel a significant recoil from the impact? We will analyze catching a flying ball as a physical collision event. Since this is a collision, the total momentum before and after the collision must be equal according to the law of conservation of momentum. Because the receiver holds onto the ball after catching it, they move together as one unit, making this an inelastic collision. There are two hidden conditions in this problem we need to look at. First, it says the receiver caught the ball at the highest point of his jump. This means the receiver's vertical velocity is zero at that moment. Remember from our lessons on free fall motion that an object at its peak is momentarily at rest, so its vertical velocity is zero. Therefore, we only need to consider the horizontal motion for this problem. Second, since the receiver jumped straight up vertically, his initial horizontal velocity is also zero. If you understand these two hidden conditions, you can solve the problem with a simple formula. First, the total initial momentum before the collision is the sum of the mass times velocity for both the receiver and the ball. As we just discussed, the receiver's horizontal velocity is zero. Now, let's calculate the final momentum after the collision. In this inelastic collision, the receiver and the ball become one unit, so the total mass is the sum of the two masses, and they move at a common velocity. By the law of conservation of momentum, the final velocity of the player and the ball is 0.0975 meters per second. Looking at this result physically, this is an extremely small velocity, so we can conclude that the player would hardly feel any recoil at all. As you saw here, the formulas for momentum and the law of conservation of momentum are quite simple. However, accurately identifying the hidden conditions in the problem description and applying them to your solution is what determines your grade on the actual exam. It takes effort to practice various types of problems and think through them on your own. Problem number 32 describes a dangerous situation where a 2,000-kilogram Cadillac is rolling slowly toward a group of children. To save them, you decide to use your 1,000-kilogram Volkswagen to have a head-on collision and stop the rolling Cadillac. The question asks at what velocity you must hit the Cadillac to bring it to a complete stop. Since the two cars collide and stay together, we will apply the law of conservation of momentum and the principles of inelastic collisions. The hidden condition here is understanding that asking for the velocity or momentum needed to stop an object is essentially asking about the impulse of the collision. This is exactly the impulse momentum theorem. First, the total initial momentum is the sum of the mass times velocity for each car. The velocity of the Volkswagen is the unknown variable we are looking for. After the collision, the two cars stick together and come to a stop, meaning the total final momentum is zero. Based on the law of conservation of momentum, the required velocity for the Volkswagen is -2 miles per hour. The reason the velocity is negative is that it must move in the opposite direction of the Cadillac's motion. Because it's a simple case, we use miles per hour as our unit, just like the problem stated. Problem number 34 is about an inelastic collision in the vertical direction. Two children are playing by jumping up and down on a trampoline. While one child is at the highest point of their jump, the second child moves upward at 4.1 meters per second and grabs the first child. The question asks for the velocity of the two children while they are holding onto each other. This is a classic inelastic collision problem. We can easily calculate the result by applying the law of conservation of momentum to the vertical motion. The hidden condition here is that the second student grabs the first student exactly when the first student is at the peak of their jump. In free fall motion, when an object is at its highest point, it is momentarily at rest, meaning its velocity is zero. So, at the moment they collide, the velocity of the first child is zero. First, the initial momentum is the sum of the mass times velocity for both children. Since one child is at the peak, her vertical velocity is zero. After the collision, meaning after they grab each other, the final momentum is the product of the total mass of both children and their common shared velocity. By the law of conservation of momentum, the final velocity of the two children is 2.32 meters per second. Just like the problems we solved today, you can solve these easily by using the law of conservation of momentum and the concept of inelastic collisions, where two objects become one with a combined mass and a common velocity. Identifying the hidden conditions in the problem description is the most important skill for the actual exam, so please review and understand many different types of problems. That's it for today's lecture. Great job, everyone, and I'll see you in the next session.